Hey there, folks. Let's talk about counting. And we've spent a little time in class today actually talking about this. But let's get it down and have it as a matter of record. And really what I want to do is review just a little bit. Let's talk about what we've talked about so far. So we've talked about the fundamental counting principle. Which basically says if you have a series of tasks that are, categorized here, and you've got so many ways to do this task, so many ways to do this task, so many ways to do this task, then the way to do the entire thing is just the product of those things. Okay? If we are dealing with an ordered selection of R things from N possible items with unlimited repeats, then fundamental counting principle would say, okay, that's N choices for this one, N choices for that one, N choices for that one, and you got R things, so this would be N to the R. Okay, we looked at some problems where we did things like that. If we talk about an ordered selection of R things from N possible items with no repeats, then we were talking about permutations in pick R. And this is N factorial divided by N minus R factorial. Okay. Then we talked about, okay, let's say we're looking at a collection of things. So an unordered collection of R things from N possible items and again with no repeats. Then we were talking about combinations. And so either use this notation C, N, R, or more commonly we use the binomial coefficient notation, N choose R. And this is basically this, but you divide the order out of it. You've got this new term in the bottom, R factorial. Okay. And we built that up over the last lecture. So now I'd like to take a look at a situation where we'd like to know the number of ways of we want to have an ordered selection of length N, so we're going back to ordered selection, but I can now have repeats. And some of my items are indistinguishable from other items, okay? So suppose count the number of ways of constructing an ordered selection of length n where some of the items are indistinguishable, big word, from each other. Okay, and I think the example I gave in class, and let me actually get this at the top of another page, was the word Tennessee. Thanks, Julian. Julian, I was looking for a good volunteer with repeated letters in it, and Julian gave me one, Tennessee. Okay. So, the question I asked in class was, how many ways can we arrange the letters in the word Tennessee? Any ways can we arrange the letters of the word Tennessee? Okay, and what we talked about was that if I were to distinguish between these letters, if I don't know what word I was going for there, if we had the characters T, but then I distinguish between the E's, you know, E1, and distinguish between the N's, N1 and N2, and E2, and S1 and S2, and E3 and E4, then it's actually an easy problem, right? I've got 9 characters, I've got 9 slots, I've got 9 choices for the first one, 8 for the second, so forth, right? But that's a big if. We don't have that. We've got N's that I can't tell apart. I've got E's that I can't tell apart, and I've got a couple S's I can't tell apart, right? So let's think about how we would do this. Really what you'd think about doing is you look at each letter and you say, okay, I've got to find a position to put this letter into, okay, or positions to put this letter into. Okay, we have 9 positions. And I should close this up by saying, however, not distinguish between multiple E's, N's, and S's. Okay, so we have 9 positions in our word, our rearrangement of those letters, okay? And I have basically 4 letters. I have 1 T. I have actually 4 E's, right? Okay. I have 2 N's. And I have 2 S's. Okay. So if we're going to build this word, and we're thinking about it, you got 9 slots over here. They're in order. The change in order would be a different word. So one way we could think about this is, all right, let's take a position and assign it to T. Okay? And so there are 9 choices there. That's pretty clear. We would think of that really as 9 choose 1, right? Or 9 pick 1. It's going to be the same answer. But in a second you'll see that the combinations is really kind of the way we're thinking. After we choose the T, a position for the T, then I could go through and choose positions for the E's. And this is where the combinations things really comes into play, because let's say I pick the first 4 positions. T's over here somewhere, and I choose the first 4 positions. Then it doesn't matter if I choose the first, second, third, and fourth position, or the fourth, third, second, and first position. It'd be the same word, right? So we really are choosing here. We're doing combinations, and I have 8 possible choices left, or 8 possible positions left, and I want to choose 4 of them. Okay, so 9 choose 1 ways of placing the T, and then 8 choose 4 choices for positions for the E, and that leaves me then actually with just 4 positions left, right? And then out of those 4, I want to choose then locations for the N's. And out of the 2 that remain, I want to choose 2 positions for the S's. And there's only one way to do that, right? So the last choice is, that last number is 1. Fundamental counting principle says, okay, you're doing a series of tasks here. Certainly I can distinguish between placing the T's and the E's and the N's and the S's. So the number of ways to do this total thing is to multiply all of these. So this is 9 choose 1 times 8 choose 4 times 4 choose 2, and then 2 choose 2, which we now need to write that out in terms of its factorials, right? So this is 9 factorial over 1 factorial, and then 9 minus 1 factorial, okay, times, and then we've got 8 factorial over 4 factorial, and then 8 minus the 4 factorial, times 7 factorial over, 4, make that a 4, factorial over 2 factorial, and then 4 minus 2 factorial, times, and then the last one here, 2 factorial over 2 factorial, and then 2 minus 2 factorial. And it occurred to me in class today that I didn't even really get into a deep conversation about factorials. I hope you've seen this, but that 9 factorial is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. The one thing that's kind of important in our calculations here is to realize that 0 factorial is not 0, it's 1. 0 factorial is 1, and that's by convention. it's a good convention because it avoids zeros in our denominators, and all the mathematics works out with it when we're talking about choosing things. So, okay, let's clean this up just a little bit. And I think you're going to see we got some nice cancellations here. We've got 9 factorial over 1 factorial and then 8 factorial times 8 factorial over 4 factorial 4 factorial times 4 factorial over 2 factorial and 2 factorial times 2 factorial over 2 factorial and 0 factorial. So actually I've got some really nice cancellations here. And then right there, those are gone. And so all we're left with in the top is this 9 factorial. Okay, and then I've got a 1 factorial and a 4 factorial and a 2 factorial and then another 2 factorial, and then 0 factorial is just 1. Okay, so that's kind of a cool little pattern that pops up if you'll spot the numbers here. 9 is the number of letters we're dealing with total. 1 is the number of T's that we're dealing with. The 4 goes to the 4 E's that we're dealing with. The 2 is the 2 N's, and then this 2 refers to the 2 S's. Okay, so there is a nice little pattern to this, and by the way, I guess we should complete this. It just occurred to me I don't have my calculator with me. Let me grab it real quick. Actually get this number. We could clean it up just a little bit. Let's see. This is 9 times 8 times 7 times 6 times 5 times 4 factorial. I'll stop there because I can get rid of my 4 factorial. Then 1 factorial is just 1. 4 factorial, they're gone. And then I've got 2 times 1 times 2 times 1. Let's see, that's 4. So this would be 9 times 2 times 7 times 6 times 5 equals, and there are 3,780 ways of arranging the letters in the word Tennessee. So that's actually a pretty decent little calculation. You know, that's again, these are the kind of things that people just automatically expect mathematicians to be able to do, right? Do these kind of crazy counting things. But what I really want to do is I want to go back and look at this and develop some notation that gets us I want to bypass this business and go straight to this next time. Okay? So let me develop a little bit of theory and a little bit of notation here. Well, theory, but the calculation we just did we can do in general. Okay? I can always do that breakdown and always get that the cancellation of those factorials. I can always get this. So we call the number of ways to arrange R1, R2, R3, whatever, on over to RK. Distinguishable indistinguishable items, like, you know, different E's, different T's, S's, whatever, into a arrangement, I should say ordered list, whatever, of length R1 plus dot 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 plus RK equals N. The multinomial coefficient denoted, and we use, just like the binomial coefficient, you know, we put the n up there. Typically we think about r below, but now we have different r's, right? So we got r1, r2, rn. Okay? And this is given by n factorial over r1 factorial, r2 factorial, on over to, and that should be a k, sorry, r sub k factorial. Okay? And the thing I pointed out in class is that really this is just a generalization of our binomial coefficient. If I had two of these things and they added up to n, so I've got r and I've got n minus r, right? If I add those up, I get n. This would just be n factorial over r factorial and n minus r factorial. That's just following this convention, right? But this is n choose r. And it's actually also n choose n minus r, which are always, these are always equivalent. But I guess what I'm saying is that with just two sets of indistinguishable things, then this just folds back into our binomial coefficient. Okay? So the homework will have you looking at a few different problems where you can use the multinomial coefficient then to calculate your answers. Now, we also talked about another thing today that does not seem related to this at all, okay? But it actually is kind of related to this, and that is the notion of, I guess I should put def here because I did define this. And I'll throw in another definition. This does not look related, but we're going to talk about how it ends up being related. A collection, so by collection I'm throwing out order. Okay, we just got a bunch of stuff of unordered items that can be repeated. Now this is in the past when we've dealt with unordered items, we were doing combinations, and with combinations you can't repeat things, right? You use an item and that's it, it's done. Now I'd like to look at something a little bit more general where we have collections, unordered items, but we can repeat things in that collection. This is called a multiset. Okay? And just for, there is notation for this. It's actually bad notation. We use brackets for everything, but I'll go ahead and use it here just so that it makes sense. Your book doesn't use the notation at all, and you won't need it for the problems, but just so I can do a little writing, I'll use it. Denoted with brackets. So, for example, if I had a multiset like that, where I have 1 and then I have the element 2 repeated 3 times, that's the same thing as if I had 2, 1, 2, 2. Okay, those are multisets. Not to be confused with what else we use these for. I forget if we use them in here, but inner products and vectors, and we use brackets too much. Okay? So the question then becomes, okay, how many different ways can we build multisets? The idea is actually quite a useful idea, and let me underline this. Multisets are much more in line with things we do in reality. I mean, if you go to, we talked about going to GADS, and I got myself all hungry in class yesterday because you go and you ask for several items, right? It's very rare that you would go in and want one of each of the, let's say you get a dozen donuts, and go in and get one of each. You typically have some repeats, right? And those are indistinguishable repeats. Yeah, you can't tell, like here, you can't tell a 2 from another 2. Well, it's the same way there. You can't tell one blueberry cake donut from another blueberry cake donut. And so we could ask the question, well, how many ways can you build a box of donuts if you are allowed to put as many blueberry cakes as you want, as many, cream filled as you want, and things like that. So let's develop a technique for counting multisets. And I think you'll see through the course of the homework and so forth, there's actually a lot of applications for being able to count multisets. So the example I used in class, now let me get a little fresh paper here because it's going to take a little space to do it. How many different multisets of size 8, length 8, can be constructed from the set, and I'll just put in like lower a, lower b, lower c. Okay? So I've got 3 items. I've got a length 8. That should be the length of my multiset. So when I'm looking at things, you know, an example of a multiset here would be A, B, C, I don't know, A, B, C again. Let's see, I need one more A. Okay, that would be a multiset where I'm taking these elements and I'm putting in. And really, if I wanted to, I could list these, because the order is not important, I could go ahead and list these things in the same order that I listed them in the set. So I'd have 1, 2, 3, 4 A's, and 2 B's, and 2 C's. Okay? Now, here's the kind of, I opened this up by saying this is related to the multinomial coefficient that we found earlier. Well, if order's not important, I could just have the convention that I always list my A's first, I always list my B's second, I always list the C's last. If I do that, then really I don't need to even list the elements, right? I just need to list places where I have the elements. So I can use just stars. okay, to denote the things in the multiset. And then when I want to distinguish between A's and B's, I just put in like a bar. And between B's and C's, a bar. Okay? Every multiset, I can do this, right? I can replace the elements that are in there with just stars and with bars. And if it's all, here's another example. What if it's all C's? C, 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 and C. Okay? Well, a bar for the A's. There's no A's. There's no B's, so another bar, and then 8 stars. And I absolutely listed one too many stars. Sorry about that. Sorry about that. 8 stars, right? So this problem then of saying, well, how many different ways can I do this, turns into how many ways can I arrange the letters in a word that has 8 stars and 2 bars. And we actually know how to solve that problem, right? We solve that problem by saying, oh, okay, well, I've got, this will have length 10, right? With 2 bars and 8 stars. The bars are indistinguishable from each other. The stars are indistinguishable from each other. And I just want to know how many ways can I arrange them. This would be 10, 2, 8. Right? Pretty cool, huh? Which actually is just 10, 2. Right? 10 factorial over 2 factorial, 8 factorial. So this is 10 times 9. Get rid of those, wonka wonka. And get rid of that. That's a 5. So that would be 45. Okay? It's that's actually a pretty cool trick, because all you're doing now is you're going through and you think, okay, here's my deal. How many different ways can I place these bars, right? And just so out of the 10 positions that you have, choose 2 to place the 2 bars, right? And that takes care of it. Okay. So that's actually that's a really neat counting trick. And you'll see that referred to sometimes as stars and bars. That's the idea behind counting multisets. I'd like to kind of summarize this now. Let's see, I don't know if I've got necessarily the room to do it. Maybe. No, let's get a fresh piece of paper. Okay. So let's kind of generalize this and build up a little bit of notation. In general, the number of multisets of size k constructed from a set of n elements I don't know if I need that, sorry, is equal to the number of lists of just two symbols. I've got the K stars that represent the elements in the multiset, and the n minus 1. Now, if you've got n different things, right, then you just need n minus 1 divisors, or as Julian pointed out, the number of commas if you list it out as a set, which is exactly right. N minus 1 bars that represent the switching from one element to another. Okay. We use the notation okay, and I call this is maybe just me that uses this, but without the second brackets there, it's n choose k, right? And I call this n multi-choose k because we're able to have things repeated, right? So n multi-choose k, we've got n things to choose from, and I want a multiset of size k. So unlike before where this number was always less than or equal to that top number, now we have the possibility that that bottom number, because we're multi-choosing, is bigger than the n. The n is telling me how many things are in my original set that I can reuse in my multiset. Okay? So let's work this out. There's got to be a kind of a clean calculation for this. Okay? If we're doing this, we're actually looking at the length of the entire thing, the stars and the bars together, right? Is, okay, we got the K stars, and then we've got the n minus 1 bars, and we are doing the multinomial then K and n minus 1. Okay, and that's the multinomial coefficient. But we've already talked about how if it's two things down here, it's really just the binomial coefficient, right? So this would be k plus n minus 1 and then just k. Okay? So that gives us a clean then method for calculating the number of multisets without having to break it down into the idea here is that we bypass the stars and bars every time and go straight to this binomial coefficient. Although, I mean, when you think about it, this is all based on that stars and bars idea. Okay, I do want to point this out that note that unlike the binomial coefficient n choose k, where k is always less than or equal to the n, okay, with the multi-choose in K, it is entirely possible that K would be greater than N. In fact, it's probably likely that the K would be bigger. In the problem that we looked at, with a set of just 3 things and multi-sets of size K, our answer would have been represented by we got 3 things and I want to multi-choose 8 of them. Okay, and what I'm saying here is that we can now go straight to the binomial. This is 8 plus 3 minus 1 in the top, and then just choose 8, right? So this is 10, choose 8, which is exactly what we ended up doing, right? Or I think maybe we said 10, choose 2 in previous work. I'm looking at it, but that's the same thing, right? This would be 10 factorial over 8 factorial and then 2 factorial. So same answer. Okay? Alright, so we've got 2 really cool counting techniques there that we can play with for a little bit. I'd like to, in the days that follow, I want to get even a little bit more complicated. But again, it's realism. I mean, if you go to get donuts at Great American, and you say, okay, I want donuts out of out of the selection blueberry cake, powdered chocolate cake, and cream filled, you're going to be really disappointed. My favorite's blueberry cake. I'm going to be really disappointed if I get home and there's no blueberry cake, right? So you probably will say things like, oh, make them out of this, but give me at least 3 blueberry cake because those are mine, and then my roommate loves the cream filled, so get at least 2 cream filled. And then, when you start putting restrictions on that, it's going to restrict this number a bit. But we need to talk about mathematically how we take care of those restrictions. Okay? So, here's our homework assignment for next time. It's in 4.4. Do problems 3 through 9 and 13 through 15. Okay? And we'll pick up on those on Tuesday. Hopefully by Tuesday I've got some of your homework, which is needs to be graded, and then I've got your tests, which need to be graded. So I got a lot of grading to do this weekend if I can get it done. We finished up with the homework for 4.2 and 4.3 in class, so I can now take that homework on Tuesday. I'll try to send out a reminder about that when all this is kind of said and done. I'll send out a reminder that the videos are up and that we can take that homework up on Tuesday. All right, that's it for me. I will see you in class.